Have you ever noticed how some days just feel different? Like time itself is playing tricks on you, moving just a fraction faster or slower than it should? Well, here's something that might blow your mind. It's not just your imagination. Our planet Earth is actually spinning faster than it has in over 50 years, and the implications of this seemingly tiny change are far more significant than you might think. On July 5th, 2024, Earth experienced its shortest day since scientists began keeping precise records. We're talking about a day that was 1.66 milliseconds shorter than the standard 24 hours. Now, before you start checking your watch wondering if you missed something, let me put this in perspective. We're dealing with changes so minuscule that you'd need an atomic clock to even detect them. But here's the fascinating part. These microscopic shifts in our planet's rotation are quietly reshaping everything from your GPS navigation to global communication networks. Picture this scenario. You're driving to an important meeting, relying on your phone's GPS to guide you through unfamiliar streets. What you don't realize is that high above you, satellites are performing an intricate dance of timing and positioning that depends on knowing exactly how fast Earth is spinning at any given moment. When our planet speeds up, even by mere fractions of a second, it throws off these carefully calibrated systems. The result? Your GPS might place you several meters away from where you actually are. For most of us grabbing coffee, that's no big deal, but for emergency responders racing to save lives or pilots navigating crowded airspace, these tiny errors could have serious consequences. But let's step back for a moment and ask the obvious question. How did we even discover that Earth is spinning faster? The answer lies in humanity's obsession with precise timekeeping. Around the world, 450 atomic clocks tick away with mind-boggling accuracy, gaining or losing only about 1 second every 100 million years. These aren't your grandmother's mantle clocks. They're technological marvels that measure time by counting the vibrations of atoms, specifically cesium atoms that oscillate exactly 9,192,631,770 times per second. It was these ultra-precise timepieces that first detected something strange happening in 2020. Instead of the gradual slowing that scientists had observed for decades, Earth suddenly started spinning faster. Not dramatically faster, mind you. We're talking about changes measured in milliseconds and fractions thereof. But in the world of atomic timekeeping, where precision matters more than almost anything else, these tiny variations represent a fundamental shift in our planet's behaviour. Now, you might be wondering why Earth's rotation speed matters at all. After all, we've been spinning for over 4 billion years, and life has managed just fine, thank you very much. But here's where things get interesting. Our modern world runs on a network of interconnected systems that all depend on incredibly precise timing. Your smartphone, your computer, the internet itself, GPS satellites, weather forecasting systems, financial markets, power grids, and even the coordination of scientific experiments all rely on synchronized clocks that agree down to billionths of a second. This level of precision became necessary because of how these technologies actually work. Take GPS, for example. Those satellites orbiting overhead aren't just floating around taking pictures. They're constantly broadcasting time-stamped signals that your phone uses to calculate your exact position. The process is elegantly simple in concept, but fiendishly complex in execution. Your phone receives signals from multiple satellites, measures how long each signal took to reach you, and uses that timing information to triangulate your location. But here's the catch. Light travels really, really fast, about 300 million meters per second to be precise. That means even a timing error of a few billionths of a second can translate into positioning errors of several meters. The relationship between Earth's rotation and GPS timing is even more intricate than you might imagine. When a satellite transmits a signal to your phone, that signal doesn't travel in a straight line through space. Well, it does from the satellite's perspective, but Earth is rotating beneath it. During the roughly 70 milliseconds it takes for the signal to reach you, our planet has turned slightly. The satellite has to account for this rotation to accurately predict where you'll be when the signal arrives. If Earth spins faster than expected, the calculations are off and your blue dot on the map ends up in the wrong place. But GPS is just the tip of the technological iceberg. Financial markets around the world depend on synchronized timing to ensure fair trading. When you buy a stock, the exchange needs to know the exact moment your order was placed relative to millions of other orders. High-frequency trading algorithms make decisions in microseconds, and even tiny timing discrepancies can mean the difference between profit and loss. Telecommunications networks use precise timing to coordinate data transmission across vast distances. Power grids synchronize their operations to maintain stable electricity distribution. Even something as simple as coordinating live television broadcasts relies on clocks that agree to within fractions of a second. The discovery that Earth is spinning faster has forced scientists to confront some uncomfortable questions about our understanding of planetary dynamics. For most of human history, we've known that Earth's rotation is gradually slowing down. This happens primarily because of tidal friction from the Moon. As our satellite tugs on Earth's oceans, creating the twice-daily rhythm of high and low tides, it acts like a cosmic brake, gradually stealing rotational energy from our planet. This process has been going on for billions of years, and it's the reason that days were only about 21 hours long 600 million years ago. The Moon's braking effect is incredibly consistent and predictable. Scientists can calculate exactly how much it should slow Earth's rotation, about 2.4 milliseconds per century. For decades, this matched observations perfectly. Earth was indeed slowing down just as the textbooks said it should. Atomic clocks confirmed that days were getting imperceptibly longer, requiring the occasional addition of a leap second to keep our human timekeeping systems synchronized with astronomical time. Then 2020 happened, and everything changed. Suddenly, instead of slowing down, Earth started spinning faster. The change was small but unmistakable. Days began getting shorter instead of longer. The trend that had persisted for decades reversed itself, leaving scientists scrambling to understand what was happening. The implications of this reversal extend far beyond academic curiosity. Our entire system of global timekeeping is built around the assumption that Earth's rotation will occasionally require us to add leap seconds to keep atomic time synchronized with astronomical time. Since 1972, 27 leap seconds have been added to Coordinated Universal Time, the standard that governs everything from internet protocols to satellite communications. But if Earth continues spinning faster, we might need to do something unprecedented: subtract a leap second. A negative leap second might sound like a minor technical adjustment, but it represents a significant challenge for global technology infrastructure. While our systems have been designed to handle the addition of leap seconds, almost none are equipped to handle their subtraction. The prospect of removing a second from time itself has engineers around the world nervous. Software systems that aren't properly prepared for this change could crash, data could be corrupted, and communication networks could fail. The irony is that we might not have time to prepare properly. Unlike positive leap seconds, which are announced 6 months in advance, the decision to implement a negative leap second would depend on Earth's rotation continuing to accelerate. And here's the unsettling truth: scientists don't fully understand what's driving these changes, which makes it nearly impossible to predict when or if a negative leap second might be needed. What we do know is that Earth's rotation is influenced by a complex interplay of factors, some predictable and others decidedly not. The Moon's tidal braking is constant and well understood. Seasonal changes in vegetation growth and atmospheric circulation create predictable annual variations. Even major earthquakes can temporarily alter Earth's rotation by redistributing mass within the planet. But the recent acceleration appears to be driven by something else entirely, something happening deep within Earth's interior that we're only beginning to understand. The leading theory points to changes in Earth's liquid outer core, a churning mass of molten iron and nickel that generates our planet's magnetic field. This metallic ocean doesn't rotate at exactly the same speed as the solid Earth above it. Sometimes it spins slightly faster, sometimes slightly slower, and these variations can affect the rotation of the entire planet through complex electromagnetic and gravitational interactions. Think of it like a spinning top with liquid inside. If the liquid sloshes around or changes its rotation speed, it affects how the entire top spins. In Earth's case, the liquid core appears to have slowed down in recent decades, and through a complicated series of interactions with the solid mantle and crust, this has caused the surface to spin faster. It's a bit like a cosmic game of conservation of angular momentum, where energy lost in one part of the system shows up as increased rotation in another. But here's where things get really interesting. Climate change is also playing a role in Earth's rotation, though not in the way you might expect. As global temperatures rise and polar ice melts, massive amounts of water are redistributing from the poles toward the equator. This is like a figure skater extending their arms during a spin. It should slow down Earth's rotation, not speed it up. The fact that Earth is spinning faster despite this climate-induced braking effect suggests that whatever is happening in the core is even more significant than scientists initially realized. We're essentially witnessing a planetary-scale tug-of-war between different forces, with the core's influence currently winning out over climate change's braking effect. This discovery has profound implications for our understanding of how Earth works as a dynamic system. It suggests that the interior of our planet is far more active and influential than we previously thought. The liquid core isn't just passively generating our magnetic field, it's actively participating in the rotation of the entire planet in ways that can override other global-scale processes. The human element in all of this cannot be overlooked. For the first time in Earth's history, our species has developed technology sensitive enough to detect these minute changes in planetary rotation, and sophisticated enough to be disrupted by them. We've created a civilization that depends on split-second timing, and now we're discovering that our planet doesn't always cooperate with our need for precision. This represents a fascinating intersection of planetary science and human technology. The same atomic clocks that allow us to detect Earth's changing rotation are also the foundation of the technological systems that could be disrupted by these changes. We've become sensitive to variations in our planet's behavior that would have been completely undetectable and irrelevant to previous generations. The story of Earth's accelerating rotation is still being written, and the next chapters promise to be just as intriguing as what we've discovered so far. Scientists around the world are working to understand the mechanisms driving these changes, while engineers grapple with the practical implications for our technological infrastructure. As we continue to monitor our planet's spin with ever greater precision, we're likely to uncover even more surprises about how Earth works as a complex, dynamic system. The relationship between our planet's interior, its climate, and its rotation is proving to be far more intricate than anyone imagined. What makes this situation even more fascinating is that we're not just passive observers of these planetary changes. Our species has inadvertently become a player in the cosmic dance of Earth's rotation, and the effects are more far-reaching than most people realize. Consider the scale of what's happening. Every single day, our planet completes one full rotation relative to the distant stars. That's roughly 25,000 miles at the equator, spinning through space at over 1,000 miles per hour. When we say Earth is spinning faster, we're talking about completing this massive journey a fraction of a millisecond sooner than expected. It's like a marathon runner finishing a 26-mile race a few steps ahead of schedule, except the runner weighs 6 trillion kilograms and the finish line is measured by atomic clocks. The precision required to detect these changes is almost incomprehensible. Imagine trying to measure the thickness of a human hair using only a ruler marked in inches. That's roughly equivalent to what scientists are doing when they track millisecond changes in Earth's rotation. The fact that we can detect these variations at all speaks to humanity's remarkable ability to push the boundaries of measurement and observation. But here's where the story takes an unexpected turn. The same climate change that's melting polar ice and redistributing water around our planet is actually working against the acceleration we're observing. As ice sheets in Greenland and Antarctica melt, billions of tons of water flow from the poles toward the equator. This redistribution of mass should slow Earth's rotation, much like a spinning figure skater extending their arms to reduce their spin speed. The physics behind this is elegantly simple. When mass moves away from Earth's rotation axis, the planet's moment of inertia increases, and basic conservation of angular momentum demands that the rotation rate decrease. It's the same principle that allows figure skaters to control their spin speed by pulling their arms in or extending them out. For Earth, melting polar ice is equivalent to extending arms outward, which should act as a brake on our planet's rotation. Scientists have calculated that climate change alone should be lengthening our days by about 1 1/3 milliseconds per century. That might not sound like much, but it's actually significant enough to compete with the Moon's tidal braking effect, which has been the dominant influence on Earth's rotation for billions of years. In essence, human activities are beginning to rival astronomical forces in their impact on planetary dynamics. The fact that Earth is spinning faster despite this climate-induced braking reveals something profound about what's happening in our planet's interior. The forces driving the acceleration must be even stronger than the combined effects of lunar tidal friction and climate change. It's like discovering that a car is speeding up even though someone is pressing on the brakes and the engine is working against a headwind. This brings us back to Earth's mysterious core, that churning mass of liquid metal thousands of miles beneath our feet. The outer core is roughly the size of Mars, filled with molten iron and nickel, heated to temperatures that would make the surface of the Sun seem cool by comparison. This metallic ocean doesn't just sit there passively. It flows and churns in complex patterns driven by heat escaping from Earth's interior and the planet's rotation. These flows generate our magnetic field through a process called the geodynamo, but they also interact with the solid Earth above in ways that can influence the planet's rotation. When the liquid core speeds up or slows down relative to the mantle, it can transfer angular momentum to or from the solid Earth through electromagnetic coupling and pressure forces at the core-mantle boundary. Recent research suggests that the liquid outer core has been slowing down over the past few decades. This deceleration has transferred rotational energy to the solid Earth above, causing the crust and mantle to spin faster. It's a bit like a washing machine with an unbalanced load, where changes in the motion of the contents affect the rotation of the entire appliance. But predicting these core dynamics is extraordinarily difficult. The processes occurring thousands of miles below the surface operate on timescales ranging from years to millennia, driven by temperature differences, chemical reactions, and fluid dynamics that we can barely observe, let alone fully understand. It's like trying to predict the weather inside a sealed box that you can't open, based only on tiny vibrations you can feel from the outside. This uncertainty has created a unique challenge for the scientists and engineers responsible for maintaining global timekeeping standards. For the first time since atomic clocks were invented, they're facing the possibility of needing to subtract time rather than add it. The prospect of a negative leap second has sparked intense debates in the international community about how to handle this unprecedented situation. The technical challenges are daunting. Most computer systems and communication networks have been designed to handle the addition of leap seconds, but subtracting time creates entirely different problems. Imagine telling a computer that the clock should skip from 11:59:58 directly to midnight, bypassing 11:59:59 entirely. Many systems would interpret this as an error and crash or behave unpredictably. The potential consequences extend far beyond inconvenience. Financial markets that rely on precise timestamps for transactions could experience chaos if their timing systems malfunction. Navigation systems could provide incorrect positions. Communication networks might lose synchronization. Scientific experiments that depend on coordinated timing could produce invalid results. Even something as simple as scheduling a video conference could become complicated if different systems handle the time change differently. Some experts argue that the solution isn't to implement negative leap seconds at all, but to abandon the entire leap second system. In 2022, the International Bureau of Weights and Measures voted to eliminate leap seconds by 2035, allowing atomic time and astronomical time to gradually drift apart. This would solve the technical problems but create new challenges for astronomers and others who need to coordinate activities with Earth's actual rotation. The debate reflects a fundamental tension between our desire for precise, predictable timekeeping and the reality that our planet doesn't always cooperate with our technological needs. Earth is a dynamic, living world with complex internal processes that we're only beginning to understand. Our civilization has become dependent on timing precision that requires us to track and compensate for every tiny variation in planetary behavior. This dependence on precision timing is relatively new in human history. A century ago, most people lived their lives without ever needing to know the time more precisely than the nearest minute. Today, our smartphones routinely synchronize with atomic clocks to maintain accuracy within milliseconds, and many of our most critical technologies depend on timing precision measured in nanoseconds. The irony is that as we've gained the ability to measure time with unprecedented accuracy, we've also discovered that time itself, at least as defined by Earth's rotation, is far less stable than we once believed. Our planet is constantly changing, responding to forces both internal and external in ways that can alter its rotation on timescales, ranging from days to millennia. Weather patterns can affect Earth's rotation by redistributing atmospheric mass. Major storms with their swirling winds and pressure changes can temporarily speed up or slow down the planet's spin by tiny amounts. The annual cycle of vegetation growth and decay moves mass between the ground and the atmosphere, creating predictable seasonal variations in rotation speed. Even the gravitational pull of other planets can influence Earth's rotation, though these effects are typically very small. What makes the current situation so remarkable is that multiple factors are simultaneously influencing Earth's rotation in different directions. Climate change is acting as a brake. The Moon continues its billions of years-long process of gradually slowing our planet. Seasonal and weather effects create short-term variations, and mysterious changes in the core are currently overpowering all of these other influences to speed up Earth's rotation. It's like watching a complex mechanical system with dozens of gears, springs, and weights all working together, sometimes in harmony and sometimes in opposition. The challenge for scientists is to understand how all these components interact and to predict what the system will do next. The story of Earth's changing rotation also highlights the interconnectedness of our planet's systems. The same climate changes that are melting ice caps and altering weather patterns are also affecting how fast our planet spins. The core dynamics that generate our protective magnetic field also influence the length of our days. The Moon that creates our tides and stabilizes our climate is gradually stealing rotational energy from Earth. Everything is connected in ways that we're only beginning to appreciate. This interconnectedness extends to human society as well. The technologies we've developed to measure and respond to Earth's changing rotation are the same ones that could be disrupted by these changes. We've created a feedback loop where our increasing ability to detect planetary variations has made us more vulnerable to them. The next few years will be crucial for understanding where this story leads. Will Earth's rotation continue to accelerate, forcing us to implement the first negative leap second in history? Will the acceleration slow down or reverse as core dynamics shift or climate effects become stronger? Will we develop new technologies that are less sensitive to timing variations, or will we become even more dependent on split-second precision? What's certain is that we're living through a unique moment in both planetary and human history. Never before has our species been able to detect such subtle changes in Earth's behaviour, and never before have we been so dependent on technologies that could be affected by these changes. We're simultaneously becoming more aware of our planet's complexity and more vulnerable to its variations. The story of Earth's accelerating rotation serves as a reminder that we live on a dynamic, ever-changing world that doesn't always behave according to our expectations or needs. Our planet has its own rhythms and cycles, some predictable and others mysterious, that continue to surprise us even as our understanding grows more sophisticated. As we continue to unravel the mysteries of Earth's changing rotation, we're likely to discover even more connections between seemingly unrelated phenomena. The relationship between climate, core dynamics, and planetary rotation is proving to be far more complex than anyone imagined, with implications that extend from the deepest interior of our planet to the satellites orbiting high above. The quest to understand these planetary mysteries has led scientists down some fascinating rabbit holes, each revealing new layers of complexity in Earth's behaviour. One of the most intriguing discoveries is that our planet's rotation doesn't just change gradually over long periods. It can also experience sudden shifts that catch researchers completely off guard. Consider what happened during major earthquakes. When massive amounts of rock suddenly shift position deep underground, they can instantly alter Earth's rotation speed. The devastating Boxing Day earthquake of 2004, for instance, redistributed so much mass within the planet that it made Earth spin faster by about 3/millionths of a second. That might sound insignificant, but in the world of precision timekeeping, it's a measurable and important change. These earthquake effects work on the same principle as a figure skater pulling in their arms to spin faster. When mass moves closer to Earth's rotation axis during a seismic event, the planet speeds up. When mass moves farther away, it slows down. The 2011 earthquake and tsunami in Japan had the opposite effect, slightly slowing Earth's rotation as the massive displacement of material shifted the planet's mass distribution. But here's what makes the current situation so puzzling. No major earthquakes have occurred recently that could explain the sustained acceleration we've been observing since 2020. The changes we're seeing are too large and too persistent to be caused by seismic activity alone. Something else is driving this phenomenon, and that something appears to be happening in the one place on Earth that's hardest to study, the deep interior. The challenge of understanding Earth's core is a bit like trying to diagnose what's wrong with a car engine while sitting in the passenger seat with the hood welded shut. We can feel the vibrations, hear the sounds, and observe how the car behaves, but we can't directly see what's happening inside. Scientists have developed ingenious ways to peer into Earth's interior using seismic waves from earthquakes, but the picture remains frustratingly incomplete. What we do know is that the outer core is an incredibly dynamic place. Convection currents flow through the molten metal at speeds of several kilometers per year, driven by heat escaping from the solid inner core and the cooling effects of the mantle above. These flows create complex patterns that change over time, sometimes strengthening in certain regions and weakening in others. These variations in core flow can affect Earth's rotation through several mechanisms. Electromagnetic forces between the conducting liquid outer core and the solid inner core can transfer angular momentum back and forth. Pressure changes at the boundary between the core and mantle can create torques that speed up or slow down the solid Earth above. Even small changes in the shape of the core mantle boundary can influence how rotational energy is distributed throughout the planet. Recent computer simulations suggest that we might be witnessing a particularly dramatic example of these core-mantle interactions. Some models indicate that the inner core, that solid sphere of iron and nickel at the very centre of our planet, might have temporarily stopped rotating relative to the surface, or even begun rotating in the opposite direction. If confirmed, this would represent one of the most significant changes in Earth's deep interior behaviour ever documented. The implications of such a change would extend far beyond rotation speed. The inner core plays a crucial role in generating Earth's magnetic field, and any significant alteration in its behavior could potentially affect the strength and stability of the magnetic shield that protects us from harmful solar radiation. While there's no immediate cause for concern, the discovery highlights just how much we still don't understand about our planet's inner workings. Meanwhile, the seasonal effects on Earth's rotation continue to provide a fascinating backdrop to these larger changes. Every year, as summer arrives in the Northern Hemisphere, billions of trees grow new leaves, moving mass from the ground up into the canopy. This redistribution of biomass actually makes Earth spin slightly slower, creating a predictable annual variation in the length of our days. The effect is small but measurable, typically changing day length by about a millisecond over the course of a year. It's a beautiful example of how life itself participates in planetary dynamics, creating rhythms that echo through the very rotation of our world. When autumn comes and leaves fall, the mass returns to the ground and Earth's rotation speeds up slightly in response. Atmospheric circulation adds another layer of complexity to these seasonal variations. The jet streams that circle our planet carry enormous amounts of air at high speeds, and changes in their intensity and position can affect Earth's rotation. During El Niño and La Niña events, when ocean temperatures shift and alter global weather patterns, these atmospheric changes can create measurable variations in how fast our planet spins. Ocean currents play a similar role, moving vast quantities of water around the globe in patterns that can influence rotation speed. The Gulf Stream alone transports more water than all the world's rivers combined, and variations in its flow can create tiny but detectable changes in Earth's angular momentum. Even the seasonal melting and freezing of sea ice contributes to these effects, as water transitions between solid and liquid states and shifts between different latitudes. All of these natural variations create a complex background against which scientists must identify the more dramatic changes we've been observing. It's like trying to hear a conversation in a crowded restaurant while multiple other conversations, background music, and kitchen noise all compete for your attention. The skill lies in filtering out the predictable seasonal and weather-related variations to identify the underlying trends that might indicate something more significant is happening. The precision required for this kind of analysis pushes the boundaries of what's possible with current technology. Those 450 atomic clocks scattered around the world don't just tick away in isolation, they're constantly compared with each other, their measurements analysed and cross-referenced to ensure accuracy. Any clock that starts drifting away from the consensus is investigated and recalibrated. The process of determining Earth's exact rotation speed involves combining data from multiple sources. Radio telescopes track the positions of distant quasars, those incredibly bright and stable objects billions of light-years away that serve as fixed reference points against which Earth's rotation can be measured. Satellite laser ranging systems bounce light off reflectors placed on artificial satellites to measure their precise positions and movements. GPS satellites themselves provide another layer of timing data that can be used to track variations in planetary rotation. All of this information gets fed into sophisticated computer models that attempt to separate the various influences on Earth's rotation and identify the underlying trends. It's a bit like trying to solve a jigsaw puzzle where some of the pieces keep changing shape and you're not entirely sure what the final picture is supposed to look like. The international cooperation required for this effort is remarkable. Scientists from dozens of countries contribute data and expertise to the global effort to monitor Earth's rotation. The International Earth Rotation and Reference System Service coordinates these activities, bringing together researchers from national observatories, universities, and space agencies around the world. This collaboration has become even more important as the implications of Earth's changing rotation have become clearer. The decision of whether to implement a negative leap second affects every country and every technology system that depends on precise timing. It's not something that can be decided unilaterally by any single nation or organization. The discussions around this decision reveal just how interconnected our modern world has become. A choice made in a conference room in Paris about global timekeeping standards can affect everything from smartphone apps in Tokyo to financial trading systems in New York to scientific experiments in Antarctica. The ripple effects of seemingly technical decisions can spread across the entire global technology infrastructure. Some of the most heated debates have focused on whether leap seconds should exist at all. Proponents argue that maintaining the connection between atomic time and Earth's rotation is fundamentally important for navigation, astronomy, and our understanding of planetary dynamics. Without leap seconds, they contend, atomic time would gradually drift away from solar time, creating long-term problems for any activity that needs to coordinate with Earth's actual position and orientation. Critics counter that leap seconds create more problems than they solve in our increasingly digital world. They point to the software crashes, communication failures, and data corruption that have accompanied previous leap second implementations. In their view, the tiny astronomical drift that would occur without leap seconds is a small price to pay for avoiding the technological chaos that these time adjustments can create. The debate has taken on added urgency as the possibility of a negative leap second has emerged. While positive leap seconds have caused problems in the past, at least software engineers had decades to develop systems that could handle them. A negative leap second would be uncharted territory, with no historical precedent to guide the development of robust solutions. Some technology companies have developed their own workarounds to avoid leap second problems entirely. Instead of implementing the time change all at once, they spread it out over many hours, making tiny adjustments to their internal clocks that gradually bring them back into alignment with standard time. This leap smear approach reduces the risk of sudden failures, but it creates its own complications when different systems use different smearing techniques. The challenge of coordinating these various approaches highlights a broader issue with our global technology infrastructure. While we like to think of the internet and related systems as seamlessly integrated, they're actually a patchwork of different technologies, standards, and implementation approaches that don't always work perfectly together. Leap seconds expose these fault lines in ways that can have far-reaching consequences. The financial implications alone are staggering. High-frequency trading systems that execute millions of transactions per second depend on precise timing to ensure fairness and prevent market manipulation. Even a brief disruption to these systems during a leap second implementation could potentially cost billions of dollars and undermine confidence in global financial markets. Telecommunications networks face similar challenges. The systems that route phone calls and internet traffic around the world depend on synchronized timing to coordinate their activities. A failure in these timing systems could disrupt communications for millions of people, affecting everything from emergency services to business operations to personal conversations. The aviation industry presents another area of concern. Air traffic control systems use precise timing to coordinate the movement of aircraft in crowded airspace. GPS-based navigation systems help pilots know exactly where they are and where they're going. Any disruption to these timing-dependent systems could potentially compromise flight safety, forcing airports to ground flights until the problems are resolved. Even seemingly mundane activities could be affected. The systems that coordinate traffic lights in major cities rely on synchronized timing to optimize traffic flow. Smart grid technologies that manage electrical power distribution use precise timing to balance supply and demand across vast networks. Online gaming platforms depend on coordinated timing to ensure fair play between participants in different locations. The cascading effects of timing disruptions can be difficult to predict and even harder to prevent. A problem that starts in one system can quickly spread to others that depend on it, creating a domino effect that amplifies the initial disruption. The challenge for engineers is to build resilience into these systems without sacrificing the precision that makes them useful in the first place. This tension between precision and resilience reflects a broader challenge facing our technological civilization. As our systems become more sophisticated and interconnected, they also become more vulnerable to unexpected changes in the fundamental parameters they depend on. Earth's rotation is just one example of a planetary variable that we've come to take for granted. only to discover that it's not as stable as we assumed. The realization that our planet's rotation can change in unexpected ways has prompted scientists to look more carefully at other supposedly constant features of Earth's behavior. Are there other planetary parameters that we've assumed to be stable but might actually be variable? Could changes in Earth's magnetic field, gravitational field, or atmospheric properties create similar challenges for our technology systems? These questions are becoming increasingly relevant as our dependence on precision technology continues to grow. The same trends that have made us vulnerable to variations in Earth's rotation are making us vulnerable to other types of planetary changes as well. Climate change, space weather, and geological activity all have the potential to affect the systems we rely on for everything from navigation to communication to power distribution. The story of Earth's accelerating rotation thus serves as a case study in the unexpected ways that planetary science and human technology can intersect. What started as an academic curiosity about tiny variations in day length has evolved into a practical challenge with implications for billions of people around the world. As we continue to monitor our planet's behavior with ever greater precision, we're likely to encounter more surprises that challenge our assumptions about how Earth works. The key will be developing the flexibility and resilience to adapt to these discoveries without sacrificing the benefits that precision technology provides. The next chapter in this story is still being written, with scientists around the world working to understand the forces driving Earth's changing rotation, and engineers developing solutions to manage the technological challenges these changes create. Whatever happens next, one thing is certain. We're living in an era when the boundary between planetary science and practical technology has never been more permeable or more important to understand. The quest to predict Earth's rotational behavior has led scientists down some unexpected paths, revealing connections between seemingly unrelated phenomena that span from the ocean depths to the edge of space. One of the most surprising discoveries involves the role of groundwater depletion in planetary dynamics. As humans pump billions of gallons of water from underground aquifers for agriculture and urban consumption, we're literally redistributing mass on a global scale. This underground water mining doesn't just affect local water tables. When groundwater is extracted and eventually flows to the oceans, it creates a subtle but measurable shift in how mass is distributed around our planet. The effect is similar to what happens when polar ice melts, moving water from one location to another and altering Earth's moment of inertia. Scientists estimate that groundwater depletion alone may be contributing to changes in Earth's rotation axis, causing our planet to wobble slightly as it spins through space. The implications extend beyond simple physics. Satellite missions designed to monitor Earth's gravitational field have detected these mass redistributions with remarkable precision. The Gravity Recovery and Climate Experiment, known as GRACE, can measure changes in Earth's gravitational field so subtle that they reveal when farmers in California's Central Valley pump groundwater, or when ice sheets in Antarctica lose mass to the ocean. These observations have revolutionized our understanding of how human activities influence planetary behavior. We're not just passive observers of Earth's systems anymore. Through our collective actions, we've become a geological force capable of altering fundamental planetary parameters. The same species that learned to measure time with atomic precision is now inadvertently changing the rate at which our planet spins. But perhaps the most mind-bending aspect of this story involves the relationship between Earth's rotation and the very fabric of space-time itself. Einstein's theories of relativity tell us that massive rotating objects like planets actually drag space-time around with them as they spin. This phenomenon, called frame dragging, means that Earth's rotation creates a subtle twist in the geometry of space and time in our immediate cosmic neighborhood. The effect is incredibly small, but it's real and measurable. Satellites in Earth orbit experience this space-time dragging, which affects their motion in ways that can be detected with sufficiently sensitive instruments. The Gravity Probe B mission spent years measuring this effect with gyroscopes so precise that they could detect changes in orientation smaller than the width of a human hair viewed from 10 miles away. What makes this relevant to our rotation story is that any change in Earth's spin rate also changes the amount of frame dragging our planet creates. As Earth spins faster, it drags space-time around with it more vigorously. As it slows down, the dragging effect weakens. This means that the tiny changes in rotation speed we've been discussing actually alter the geometry of space-time itself, creating ripples that propagate outward at the speed of light. The precision required to detect these effects pushes the absolute limits of human measurement capability. We're talking about changes so small that they make the proverbial needle in a haystack seem like a billboard by comparison. Yet somehow, through a combination of brilliant engineering and mathematical wizardry, scientists have learned to measure these effects and use them to better understand how our planet behaves as a massive, spinning object in the cosmos. This level of precision has revealed other unexpected connections between Earth's rotation and phenomena we never imagined could be related. Solar activity, for instance, can influence our planet's rotation through complex interactions between the solar wind and Earth's magnetic field. When the Sun experiences particularly intense magnetic storms, the charged particles it hurls toward Earth can interact with our magnetosphere in ways that create subtle changes in atmospheric circulation patterns. These atmospheric changes in turn can affect Earth's rotation speed through the same mechanisms that create seasonal variations. It's like a cosmic game of telephone where solar storms whisper to Earth's magnetic field, which speaks to the atmosphere, which eventually affects how fast our planet spins. The chain of causation is so indirect and subtle that it took decades of careful observation to identify these connections. The discovery of these solar influences has added yet another layer of uncertainty to predictions about Earth's future rotation. Not only do we need to account for core dynamics, climate change, and tidal effects, but we also need to consider the Sun's 11-year activity cycle and the possibility of unpredictable solar events that could temporarily alter our planet's spin rate. Space weather forecasters now find themselves in the unusual position of needing to consider how solar storms might affect not just satellite communications and power grids, but also the fundamental rate at which Earth rotates. It's a reminder that our planet doesn't exist in isolation, but is part of a dynamic solar system, where events on the Sun can have measurable effects on the most basic parameters of our world. The increasing sensitivity of our measurements has also revealed that Earth's rotation responds to phenomena occurring on timescales ranging from hours to millennia. Atmospheric pressure changes during major storms can create temporary variations in rotation speed that last for days or weeks. Tidal forces from the Sun and Moon create variations that follow predictable astronomical cycles. Core dynamics produce changes that can persist for decades or centuries. Layered on top of all these natural variations are the growing effects of human activities. Climate change continues to redistribute mass through ice melting and sea level rise. Reservoir construction and groundwater extraction move water around the planet. Even large-scale engineering projects like building dams or draining wetlands can have measurable effects on Earth's rotation when they involve moving significant amounts of mass. The challenge for scientists is to disentangle all these different influences and understand how they interact with each other. It's like trying to conduct an orchestra where every musician is playing a different piece of music. Some are improvising, and new instruments keep joining the ensemble without warning. The goal is to predict what the overall sound will be, but the complexity makes long-term forecasting extremely difficult. This complexity has led some researchers to question whether precise, long-term prediction of Earth's rotation is even possible. The system may be fundamentally chaotic, meaning that tiny uncertainties in our understanding of current conditions could lead to dramatically different outcomes over time. It's similar to the challenges faced by weather forecasters, who can make reasonably accurate predictions for a few days but struggle with longer-term forecasts because the atmosphere is inherently unpredictable. The implications of this uncertainty extend far beyond academic interest. If we can't predict Earth's rotation with confidence, how can we plan for future leap-second implementations? How can we design technology systems that will remain accurate over decades? How can we ensure that critical infrastructure remains synchronized as planetary conditions change in unpredictable ways? Some engineers argue that the solution is to build more flexibility into our systems rather than trying to predict planetary behavior with impossible precision. Instead of designing technology that depends on knowing Earth's exact rotation rate years in advance, they advocate for systems that can adapt quickly to changes as they occur. This approach treats planetary variability as a feature of the environment that must be accommodated, rather than a problem to be solved through better prediction. Others contend that abandoning the quest for predictive accuracy would be premature. They point to the remarkable progress that has been made in understanding Earth's rotation over the past few decades, and argue that continued research will eventually reveal the underlying patterns that govern these changes. In their view, what appears chaotic today may prove to be predictable tomorrow with better models and more complete data. The debate reflects a broader tension in how we approach the challenge of living on a dynamic planet. Do we try to predict and control natural variability, or do we learn to adapt and flow with changes as they occur? The answer may depend on the specific application and the level of precision required. For some uses, adaptive approaches may be sufficient. GPS systems, for instance, already incorporate real-time corrections that account for current atmospheric conditions and satellite positions. Adding corrections for Earth's rotation variations would be technically challenging but not impossible. Financial trading systems could potentially build in safeguards that pause operations during leap-second implementations to avoid timing-related errors. But other applications may require more predictive approaches. Long-term space missions that depend on precise navigation over years or decades need to account for Earth's rotation changes in their planning. Scientific experiments that require coordination between observatories around the world may need advance notice of timing adjustments to ensure proper synchronization. The diversity of requirements has sparked discussions about whether a one-size-fits-all approach to timekeeping makes sense in our increasingly complex technological landscape. Some propose developing multiple time standards optimized for different applications, much like we already have different coordinate systems for different types of mapping and navigation. Such a system might include an ultra-stable atomic time standard for applications requiring maximum precision, a solar time standard that tracks Earth's actual rotation for astronomical observations, and various hybrid standards that balance stability with astronomical accuracy for different technological needs. Users could choose the time standard that best matches their requirements, rather than trying to force all applications to use a single compromise solution. The challenge with multiple time standards is ensuring interoperability between systems that use different standards. Already, the coexistence of GPS time, UTC, and various national time standards creates occasional confusion and compatibility problems. Adding more standards could exacerbate these issues unless careful attention is paid to conversion algorithms and interface protocols. The international nature of modern technology makes coordination even more critical. A timing standard adopted by one country or region can quickly become a de facto global standard if it's widely used in international commerce or communication. The risk is that ad hoc solutions developed for specific problems could fragment the global timing infrastructure in ways that create new problems down the road. These coordination challenges highlight the importance of international scientific cooperation in addressing the implications of Earth's changing rotation. The decisions made today about how to handle timing variations will shape the technological landscape for decades to come. Getting them wrong could create systemic vulnerabilities that affect everything from navigation to communication to financial transactions. The story of Earth's accelerating rotation thus serves as a fascinating case study in how scientific discovery and technological development intersect in unexpected ways. What began as an academic curiosity about planetary dynamics has evolved into a practical challenge that touches nearly every aspect of modern life. The solution will require not just scientific understanding, but also engineering innovation, international cooperation, and careful consideration of the trade-offs between precision and adaptability. As we continue to push the boundaries of measurement precision and technological capability, we're likely to encounter more situations where the natural variability of our planet challenges our assumptions about stability and predictability. The key will be developing the wisdom to know when to seek greater precision and when to embrace uncertainty as an inherent feature of living on a dynamic world. The next phase of this story will likely involve a combination of continued scientific research into Earth's rotation mechanisms and parallel development of more robust technological systems that can handle planetary variability without compromising functionality. Success will require bringing together expertise from fields as diverse as geophysics and software engineering, astronomy and network architecture, climate science, and financial system design. What's certain is that we're living through a unique moment in the intersection of planetary science and human technology. Never before have we been able to measure Earth's behavior with such precision, and never before have we been so dependent on technologies that could be affected by planetary variations. How we navigate this intersection will shape both our understanding of our planet and our ability to build resilient technological systems that can thrive in an inherently variable world. The implications extend beyond immediate practical concerns to fundamental questions about humanity's relationship with the planet we inhabit. As we become more aware of Earth's dynamic nature and our growing influence on planetary systems, we're forced to reconsider our role as both observers and participants in the cosmic dance of planetary evolution. This awareness brings both responsibility and opportunity. The same precision that allows us to detect Earth's changing rotation also enables us to monitor and potentially mitigate our impacts on planetary systems. The technologies that are vulnerable to rotation variations are also tools that could help us better understand and respond to other forms of planetary change. But the challenge will be learning to live consciously and responsibly as a planetary force, while maintaining the technological capabilities that define modern civilization. It's a delicate balance that will require wisdom, humility, and a deep appreciation for the complex and often surprising ways that human activities and natural processes interact on our remarkable planet. The quest to understand and adapt to Earth's changing rotation represents more than just a technical challenge. It's a profound reminder that we live on a planet that refuses to be taken for granted, one that continues to surprise us even as our understanding grows more sophisticated. Every day, as you check your phone for the time or follow GPS directions to a destination, you're participating in a global system that must constantly adjust to the subtle rhythms of a world in motion. The precision required to track these planetary variations has pushed human ingenuity to remarkable limits. Consider that the atomic clocks monitoring Earth's rotation are so accurate that if you had started one at the birth of the universe, it would be off by less than a second today. Yet even this extraordinary precision barely captures the delicate dance between our planet's core, its climate, and the cosmic forces that shape our daily experience of time. What makes this story particularly compelling is how it reveals the hidden connections between the grandest scales of planetary physics and the most mundane aspects of modern life. The same forces that generate Earth's protective magnetic field deep within our planet's molten core also influence whether your morning commute navigation system guides you to exactly the right parking spot or leaves you circling the block in confusion. These connections extend in directions that continue to surprise researchers. The water you drink, the food you eat, even the air you breathe are all part of a global mass distribution system that subtly influences how fast our planet spins. When farmers in distant countries irrigate their crops, or when ice melts in regions you'll never visit, these changes ripple through the planetary system in ways that eventually affect the atomic clocks that keep your digital life synchronized. The human element in this cosmic story cannot be overstated. We've become both the most sensitive detectors of planetary change and potentially the most significant drivers of that change. Our species has developed the capability to measure variations in Earth's rotation that would have been completely undetectable to our ancestors, while simultaneously engaging in activities that can influence those very measurements. This dual role as observer and participant creates fascinating feedback loops that scientists are only beginning to understand. The same industrial activities that contribute to climate change and affect Earth's rotation also power the technological infrastructure we use to monitor these changes. We're studying a system that we're simultaneously altering, using tools that depend on the stability of the very phenomena we're investigating. The philosophical implications are as intriguing as the practical ones. What does it mean to live on a planet whose fundamental parameters we can both measure with extraordinary precision and inadvertently alter through our collective actions? How do we balance our need for technological precision with acceptance of the inherent variability of the natural world? These questions become more pressing as our dependence on precision timing continues to grow. The Internet of Things promises to connect billions of devices that will need to coordinate their activities with split-second accuracy. Autonomous vehicles will navigate roads using positioning systems that depend on knowing exactly where Earth is in space at any given moment. Smart cities will manage everything from traffic flow to energy distribution, using networks that require synchronized timing to function properly. Each new layer of technological sophistication makes us more sensitive to variations in planetary behavior, while simultaneously making us more dependent on the stability of the systems we're building on top of an inherently dynamic foundation. It's like constructing an increasingly elaborate house of cards on a table that occasionally trembles, then developing ever more sensitive instruments to detect when the table moves. The international cooperation required to manage these challenges reflects the global nature of both the technology and the planetary phenomena involved. Earth's rotation affects everyone equally, regardless of political boundaries or economic systems. The atomic clocks in different countries must agree with each other. The satellites overhead serve users around the world, and the decisions about leap seconds impact every connected device on the planet. This shared vulnerability has fostered remarkable collaboration between scientists and engineers who might otherwise have little reason to work together. Astronomers studying distant quasars collaborate with telecommunications engineers managing fiber optic networks. Geophysicists investigating Earth's core dynamics share data with software developers debugging timing algorithms. Climate researchers tracking ice sheet changes coordinate with financial analysts concerned about trading system reliability. The urgency of finding solutions has accelerated innovation in unexpected directions. Engineers are developing new approaches to distributed timekeeping that could make systems more resilient to sudden changes. Computer scientists are creating algorithms that can adapt to timing variations without compromising functionality. Physicists are exploring whether alternative definitions of time might be more stable than our current Earth-based standards. Some of the most promising developments involve learning from natural systems that have evolved to handle variability and uncertainty. Biological organisms manage to coordinate complex activities despite operating in environments where timing precision is impossible to maintain. Social systems like markets and traffic flows often function effectively despite the absence of centralized control or perfect information. These natural models suggest that resilience might be more important than precision for many applications. Instead of trying to eliminate variability, we might be better served by designing systems that can thrive in the presence of uncertainty. This approach treats planetary dynamism as a feature of the environment to be accommodated, rather than a problem to be solved. The transition toward more adaptive systems won't happen overnight, and it won't eliminate the need for precision in applications where accuracy is genuinely critical. Scientific research, navigation, and communication will continue to require the most accurate timing possible. But for many everyday applications, a shift toward greater flexibility could reduce our vulnerability to planetary variations while maintaining the functionality we depend on. The economic implications of this transition are substantial but difficult to quantify. Building more resilient systems typically requires additional investment upfront, but can prevent much larger costs from systemic failures later. The challenge is that the benefits of resilience are often invisible until they're needed, making it difficult to justify the expense of prevention compared to the certainty of current costs. Insurance companies and risk management professionals are beginning to grapple with these trade-offs as they try to assess the potential costs of timing-related failures. How do you price the risk of a negative leap second when it's never happened before? How do you weigh the cost of building redundancy into timing systems against the probability that it will ever be needed? The answers to these questions will shape how society prepares for the challenges posed by Earth's changing rotation. Will we invest heavily in prediction and control, trying to anticipate and manage planetary variations before they can disrupt our systems? Will we focus on building adaptive capacity that can respond to changes as they occur? Or will we pursue some combination of both approaches, tailored to the specific requirements of different applications? The path forward will likely involve continued parallel development along multiple tracks. Scientific research into Earth's rotation mechanisms will continue, driven by both practical needs and fundamental curiosity about how our planet works. Engineering efforts will focus on building more robust systems that can handle timing variations without compromising functionality. International cooperation will expand to address the global coordination challenges posed by planetary-scale phenomena. Public awareness of these issues will also play an important role in shaping our collective response. Most people remain unaware that Earth's rotation speed varies or that these variations could affect the technologies they use daily. As understanding grows, it may influence everything from consumer choices about which technologies to adopt to political decisions about research funding and international cooperation agreements. Educational institutions will need to adapt their curricula to prepare future scientists and engineers for a world where planetary variability is a constant consideration rather than a distant academic concern. Students will need to understand not just how to measure and predict natural phenomena, but also how to design systems that can function effectively in the presence of uncertainty and change. The story of Earth's accelerating rotation ultimately serves as a microcosm of the broader challenges facing human civilization in the 21st century. We live in an era of unprecedented technological capability and global interconnection, but also of increasing awareness that the natural systems we depend on are far more dynamic and complex than we previously understood. Climate change, biodiversity loss, resource depletion, and space weather all present similar challenges to the ones posed by rotational variations. In each case, we're discovering that phenomena we once considered stable or predictable are actually variable and potentially influenced by human activities. The solutions will require similar combinations of scientific understanding, technological innovation, international cooperation, and adaptive management. The skills we develop in responding to Earth's changing rotation will likely prove valuable in addressing these other challenges as well. Learning to build resilient systems that can function in the presence of uncertainty, developing international cooperation mechanisms that can coordinate responses to global phenomena, and balancing the needs for precision and adaptability are all capabilities that will serve us well in navigating an increasingly complex and interconnected world. As we continue to monitor our planet's spin with ever greater precision, we're sure to encounter more surprises that challenge our assumptions and force us to adapt our technologies and institutions. The key will be maintaining the curiosity and flexibility to learn from these discoveries while building the resilience to thrive despite the uncertainties they reveal. The next time you glance at your phone to check the time, remember that you're witnessing the culmination of a remarkable human achievement. That simple digital display represents our species' hard-won ability to measure time with extraordinary precision, track the subtle variations in our planet's behavior, and coordinate activities across the globe despite the inherent dynamism of the world we inhabit. But more than that, it represents our ongoing adaptation to life on a planet that continues to surprise us, challenge us, and remind us that we're part of something much larger and more complex than ourselves. Earth's changing rotation is just one note in the grand symphony of planetary dynamics, but learning to dance to its rhythm may be one of the most important skills we develop as we venture further into an uncertain but endlessly fascinating future. The precision of atomic clocks, the complexity of global coordination, and the mystery of our planet's deep interior all come together in this seemingly simple question of how fast Earth spins. As we've discovered, the answer is both more precise and more uncertain than we ever imagined, reflecting the beautiful complexity of the world we call home and the remarkable ingenuity of the species trying to understand it. In the end, Earth's accelerating rotation tells us as much about ourselves as it does about our planet. We are a species capable of measuring time to the nanosecond while living on a world that refuses to keep perfect time. We build technologies that depend on precision while inhabiting a universe that thrives on change. And perhaps most remarkably, we continue to find wonder and meaning in the challenge of understanding our place in this cosmic dance, 1 millisecond at a time. 1 millisecond at a time.